where are we? Last time we started talking about Dirichlet characters, right? Dirichlet characters. Now we will eventually need some representation theory. So I thought this is a good soft get our toes in the water. I'm not assuming you've seen. I'm not assuming that you've seen representation theory. How many of you have seen representation theory? Out of curiosity. Okay. Okay. Not everyone. Not everyone. Good. So Dirichlet characters, we said were functions chi from Z mod NZ cross to C cross initially, right? I want to explain these things from another viewpoint, which I hope won't bore the people who already know a lot about Dirichlet characters from the analytic number theory side. Okay, so here's the representation theory viewpoint. What we really have is we have a group G. G is Z mod NZ cross. Okay, let's say N is whatever. What did we do last time? 12 or something? Just so it's not a prime power. So then G is 1, 5, 7, 11. Okay, and what we're really doing is we're taking L2 of G. What does L2 of G mean? I mean, d mu with respect to a measure mu. What does this mean? This means functions. This is the space of functions from G to the complex numbers, such that what measure do we have on this space with 4 elements? The uniform measure, such that if I take F, well, I'll write it like this. But what I really mean is a sum over A in G, F of A squared, that this is finite. And of course,
I have good news.
Yes, me too. So this is just C to the size of G, right? I just pick, for every element, I just pick a complex number. That's the space. There's nothing interesting about this space. What's interesting, so far so good? In other words, here's a sample function here. I have to tell you what it does to 1, to 5, to 7, and to 11. So it sends 1 to pi, it sends 5 to root 2, it sends 7 to I, and it sends 11 to -1. Okay, that's a function. Okay, now this function is also a Hilbert space. This I'll call it V. This is a Hilbert space. Hilbert space. I have an inner product, right? If I have two functions, F and G. Let me use G for elements of G. If I have two vectors, I'm going to keep speaking of vectors in terms of these are vector spaces of functions. So I'm going to say these are two vectors, F and G. The inner product on them is the obvious thing. You integrate F times F bar d mu over G, which again just means in our context sum over the elements of G, F of A, F prime bar of A. Kirill, I'm
You just missed the bar.
here. Thanks. Okay. So far, so good. So I'm saying very, very simple things in very, very fancy language, so that when that fancy language, so we get used to the fancy language, and when we see fancy things sitting in there, we're more comfortable with it. Okay, now we have G. Let me slow down. Some people are still writing. Okay, so G, the group G, acts on V itself. So this is what a representation is. So the pair, some people write pi. Pi is GV, G comma V. The pair, a group and an action and a representation on a vector space. This is a representation. In other words, well, let me, before I give you the formal definition, how am I going to take functions and make new functions out of them using G itself? So if I have a function like this function, I have my function F, and I'm supposed to get a new function, let's call it pi GF, which I'll write as like F sub G maybe.
This is V is just
That's right. Yes. In finite dimensional space, everything is we're not going to see, maybe I'll try to do an example. It's dangerous to do these things live, but I'll maybe try to do an example that is where G is not abelian, and so things become less trivial. Okay, so what's the action? In other words, what do I do to an element? So this is a function, this is a new function, which means it takes elements of G, right? G is in G. For every element of the group, I'm supposed to take a function and get a new function. So what is the value of this new function at some other element H in G? Can you think of a way of getting a complex number out of these two pieces of data? F already takes elements of G and returns complex numbers. F of GH is a great idea. F of GH almost works. F of G inverse H also works. I'm going to do F of HG so I don't have to write inverses. So this is called the right regular representation. Right regular as opposed to the left regular representation. Okay. Sorry? Did I misspell representation? I mean, I hardly spelled it as is.
Love those anti-representations.
The anti-representations. But you always use right regular representations for some reason. Oh, it's because on the left we want to mod out by a discrete group. So it's more fun to put them on the right. I don't know. I always put them on the right.
GH, then it's like an anti.
It's an exactly. So what does it mean to be a representation? What does it mean to act on something? Right? What I want, in other words, i.e., for all G in G, we get something called pi G or rho G, whatever. Pi G is an element of the automorphism group of V. And maybe we want this representation to be unitary. So then it's in unitary, it's an isometry of V. Okay. Okay, I'm starting to lose you, so let's do some concrete examples. So what is F sub 5? F sub 5 will take the elements 1, 5, 7, and 11 and return the complex numbers. Well, before I can return the complex numbers, let's see what it's going to do. It's going to give me the values of F, not at 1, but at 5. Not at 5, but at 25, which is 1 mod 12. Not at 35, but at 36, but at 11, right? And not at well, this is -1, so -5 is 7. 55, I can't do that. 55 plus 7 is 62. Yeah, it should be 7. 5 times 11 is 55.
48 plus 7 is.
Thank you. I'm adding 7 instead of subtracting 7. Thanks. This is why it's dangerous to do these things in public. Okay, F of 5 was √2. F of 1 was pi. F of 11, hopefully this pi and that pi don't confuse anybody. F of 11 is -1, and F of 7 is I.
Can you say what F was again?
F is in L2 of G. In other words, it's just a function. L2 has no meaning. G is a finite set. So it's just a function taking values in the group and returning complex numbers. Your favorite one.
There's no integrability.
The integrability thing is that the sum of a finite set of numbers is finite. But its sum of finite set of numbers, complex numbers, is always finite. So it's just C to the size of the group. Okay, so I took this function F, which I made up at random. Here's what the element 5, so this we could also write as pi 5 F, is the function F, a new function, F sub 5. It takes 1, 5, 7, 11 and maps it to these complex numbers. Okay, now, so we've implicitly taken a basis for this vector space. So I call this the group basis. The group basis for V is the basis, 1. By 1, I mean the function. By 1 in G, I mean the function F that takes 1 if G is equal to 1 and 0 elsewhere. Right? So that's implicitly what we've done. We've written things in the basis 1, 5, 7, 11. And it moves 1 and 5 and 7, 11 around in this funny way. And what we would like is to find, we want to find a better basis, for the action of G, so that things don't move around quite as much. This is like, it's just linear algebra, except now we have a group's worth of linear transformations. We want simultaneously all of them to act nicely. That's the only difference between linear algebra and representation theory. You don't have one map, you have lots of maps, and you want all of them to kind of be compatible with one another. Okay, so those are called, okay, so definition, a representation, so a subspace, if I have a subspace, linear subspace, these are subspace vector spaces, this is a subspace, and so if G, if G acting on W is contained in W, if G preserves W, i.e. For all G in G and for all W in W, pi G W, right? G takes elements of this vector space, but W is a subspace of that, and spits out other elements. So this is just going to be some other element of V. I want it to lie in W. This is contained in big W. Okay, so the picture is I have some space V, I have some subspace W. Now G, the group G, is moving all the elements around in funny ways, but it only takes elements of W and moves them to other elements of W. If this is an element of W, then pi G is also in W for every element of G, right? Then we say, if G preserves W, then we say GW is a sub-representation of V. Right? Makes sense. And what does it mean to be irreducible? If you don't have any proper sub-representations. So pi, I guess I'll try to say W. I'll try to stick to W for subspaces that might have interesting properties, and V for the big L2 space, the big regular representation. So far, so good? Have I lost anyone? We're saying fancy words, but we're gonna.
Everything that takes G to GL and V.
Yes. Yes, exactly. Pi maps G to GLV. Whatever the dimension of V is. Yeah. Yep. Did I ever say what it means to be a representation or what it means to be an action? I don't think I said that. So this is supposed to be a homomorphism. It's supposed to satisfy, if I take pi of GH, that should be pi of G times pi of H, composed with pi of H. These are both, if you want to think about it as matrices, or if you just want to think about them as abstract linear operators. Does that make sense? And so if I put GH here instead of HG, this wouldn't be true because then I would get pi GH applied to F would be, let's say at another element, I don't know, K, it would be F of GHK if I put it on the left. But if I did pi H first, what am I trying to say? If I put things on the right, yeah. Right. I want to do pi of G. Yes, I'm sorry. This is supposed to go in the order of the group, right? This is supposed to be pi of G. Thank you. It's supposed to be, if you're supposed to do G then H, then you should do G then H. You should apply G, then you should apply H. Guess what I'm defining as an anti-representation. That.
This, your group element.
I'm putting the group element in my example,
GHK, right?
GHK, yes.
You really should have K, GH.
Well, I'm claiming that that's the correct way to do it.
Oh.
I'm claiming that I want the right regular representation.
I feel like you justified one thing right regular representation in terms of wanting the right regular.
I guess so. I want G to act first, and then I want H to act. Not the other way around. If I did it the other way around, then it would be H hitting K first, and then G hitting it. But it should be G going first, then H, because that's what's happening in the group. Yeah, I'm justifying the right. I want this to be multiplication on the right here. I want to think of this as multiplication on the right, and so therefore I'm defining this. Fine. Let's stick to the right regular representation because
So it's not a Hom, it's
yes, it's an anti-Hom. I want G to act first, and then I want H to act. And so G should act first, and then H should act. Okay.
I think I was saying if you click unravel them, the variables, you actually follow everything up to because you're acting on the function.
I'm acting. Very good, very good. I want to act on the function, right, and not just on this. So when I act on the function, if you unravel what this says, let me not try to write it down because I'm sure I'll get it wrong. This isn't supposed to be subtle. This is supposed to be the easy part. Just getting the action right. Absolutely, I should be acting on the function. Thanks. It's the correct group representation where I don't have to put an inverse. Because if I put it on the left, then I need to put an inverse. All right. So we're up to this. So if you have a subspace that's being preserved by the group action, then that's a sub-representation. And we say is irreducible if it has no proper meaning it's not the whole space and it's not the zero vector, has no proper G invariant subspace. G invariant subspace. So if G preserves, then this is a sub-representation, and we say W is G invariant. So far, so good. Let's see what's going on for in our example. Back to our example. Our example, V is L2 of G, where G is Z mod N cross and N is 12. Okay, so the number of elements is 4. Can we think of any proper subspaces that are preserved under the action of G? So G multiplication by G is permuting all of the elements, right? Depending on which element you use to do that permutation, like 1, 5, 7, 11 under 5. So 5 sends this to the permutation, well, whatever it was, 5, don't make me do it again, 25 is 1, 7 is 35 is -1, and that's 7, right? That's a permutation, so it acts on the functions as well, and we get a different permutation. I mean, we could write this as a matrix. Maybe all of these viewpoints are useful. So this is pi 5. Pi 5 in the basis, in the group basis. Pi 5 sends 1 to 5. It sends 5 to 1. It replaces 7, 11. Okay. And is there some subspace in the group basis, for example, that is preserved? You're going to permute all the elements around. Can you think of something that's going to be invariant under that? The zero subspace, yes. So that we're not interested in because we want proper subspaces. Proper means not zero and not the whole thing. One plus 5. Is 1 plus 5 always preserved? Let's think about that. Under 5, 1 plus 5 is preserved, but what does 7 do? 7 takes 1, 5, 7, 11 to 7, 35 is -1, 49 is 1, and that's got to be 5. Sorry?
It's 5 of them.
No.
Oh, I see.
This is Z mod 12, which is Klein 4 group. Yeah. Yeah, very good. Very good. I mean, this is one of the reasons, I don't know. I just randomly picked 12, but it's a good thing I did because we don't have a generator. So the subspace 1 plus 5, the subspace generated by the vector 1 plus 5 is not preserved. 5 does keep it in house, but 7 moves it around. 7 moves 1 and 5 to 7 plus 11. But there's an even simpler vector that is preserved. Sum all of them. Yeah, let's sum all of them. Let's call this E1, which is 1 plus 5 plus 7 plus 11. Should I write indicator of 1? By this, I mean the indicator of 1 plus the indicator of 5 plus the indicator function of 7 plus the indicator function of 11. In other words, the vector of all 1s. The constant function. This is the constant function. This is the constant function. I take any element of the group and I return 1. Well, any element of G just permutes things. And so if I added them up to begin with, I mean, this is the subspace with eigenvalue 1. Right? So this is invariant. This is this. In other words, this. What's this? This is the space. W1 is the space generated by E1. E1 is a single vector, so we have the whole single line in the direction of E1. This is a subspace, and it's invariant and G invariant. So good. Can we find others? So I claim that, so let's prove a little theorem. Claim if W is a subspace of V and G invariant, and the action is, and we have a unitary representation, and pi is unitary, We know what unitary means? Unitary means it's an isometry. Unitary means we have an inner product, we have a Hilbert space, V. So we have an inner product of V and W. So for all V and W in V, and for all G in G, if you take the inner product, or you move both by G, and you take their inner product, those complex numbers should be the same. Okay, so it's an isometry. This inner product is how you measure angles, and so all angles are the same. Does that make sense? Curious, something you don't like. It's okay.
We're choosing what's the product? I mean, you're just doing complex one.
Yep. On L2, our inner
Oh.
product is this. So we're just going to take functions and multiply them together. So if W is a G invariant subspace, I claim, then so is W perp. Okay, so i.e. V splits as W. You can take off the perp space. So we had a 4-dimensional space. We found an invariant subspace. We can take the orthogonal complement to that invariant subspace and look for more invariant subspaces among the 3 dimensions left over. That's what we're doing.
But why does it matter if you have a gene in the product in there?
Oh, that it's unitary? Well, I mean, you just define if it's finite. So all of these things are a little bit easier to do in the setting of finite dimensional vector spaces. We will soon need to handle infinite dimensional vector spaces and representations on them. And so then I want to make sure that we have unitary ones where we'll have to think about when integrals converge, and being L2 will no longer be a trivial question. I mean, maybe I should already say here, decomposing. So the main object in representation theory is to decompose L2 of G into irreducibles. We've defined what it means to be an irreducible. let me finish this proof and say that fact. So we have this G invariant subspace. I claim that if you were in the perp, then then the G action keeps you in the perp. Okay, so we're given some well, what does it mean to be W perp? Recall, W perp is the set of all V in V, so that for all W in W, the inner product of V and W is 0. Okay, so take any V in V perp and take any G. Take any G in our group. We claim, the claim is that if I act by G on V, I'm still in W perp. If I started in W perp, G moves things around just to elements of W perp. So that's true if and only if for all W in W, pi G V W is equal to 0. That's what we're trying to prove. Okay. But we have an isometry, we have a unitary representation. So this is equal to, I'm going to apply pi G inverse to both sides. And that will not change the inner product because this is an isometry. So this is unitary. Unitary. Pi is unitary. Okay. Pi is in action, which means I get to cancel this and action. And now I have V inner product pi G inverse of W. But this is in W since W is invariant. W is G invariant. And V was originally in W perp. Its inner product with any element of W is supposed to be 0. So its inner product with this element of W is also 0. This is because V is in W perp. And that tells us that pi GV is also, that implies pi GV is also in W perp, which is what we want. Okay, so we can sort of peel off irreducible subspaces one by one. And if we have a finite dimensional space, eventually we'll stop. And if you, right, so either your space is already irreducible, if not, it has some reducible, it has some proper subspace, and then peel off. It's just like prime factors. Why are numbers products of primes? Not necessarily uniquely. Right? We don't know yet about the uniqueness of the decomposition of L2G into irreducibles. Okay, so main goal of representation theory would be decompose things like L2 of G into irreducibles and stitch them back together. Why would you want to do such a thing and then stitch representations back together? Why would you want to do such a thing? So let's see some examples. Okay, when G is the circle, S1, inside the complex numbers, right? Things of absolute value 1. I mean, I can think of this as R mod Z and identify this with R mod Z. So that's a nice group. What is L2 of G? With what measure? Now, the big measure. Sorry? That's right, the irreducibles. So this decomposes as now an infinite sum, n in Z, of vector spaces spanned by En, where En of X is e to the 2 pi I and X. These are the irreducible subspaces. Now there's infinitely many of them. We have a continuous group, but there's a discrete set of them. And any function in here can be recovered by summing over n of the projection of f onto this vector space times the vector space. That's Fourier analysis on the circle is just the decomposition of L2 of the circle into irreducibles. Does that make sense? when G is R itself. Kirill, something you don't like.
No, I just want to clarify that.
Please.
In the first example, we just look at the real functions on the line. This is the composition sign.
Yes.
Because it's very simple.
Oh, thank you. Yes. I hope it doesn't, I was hoping it wouldn't look too mysterious. I mean, this is just the Fourier transform at n. That's exactly what the Fourier transform is doing on the circle. In fact, it's the same thing as what it's doing on the real line with some subtleties. So L2, now L2 actually has meaning. I mean, here L2 of the circle, you know, I mean, you could blow up, I suppose, and not be integrable. You have to do something even on a finite interval. Now we have an infinite interval over which to worry. So L2 G mu is exactly the same as L2 of R, which we'll take measure. How does this decompose? Well, this still decomposes not into a direct sum, but a direct integral over Xi in R of subspaces spanned by EC, where EC of x, these are functions, e to the 2 pi I x c. Now, these functions are not in L2. These themselves are not, obviously, in L2, are not in our vector space. But they're almost in L2, in the sense that they occur in the spectral resolution of the Laplace operator acting on this. So when you try to decompose L2G into irreducibles, what does that mean? Well, the irreducible, they would be subspaces if any of the functions were in L2, but you still have a Fourier inversion formula. The Fourier inversion formula is exactly, from this viewpoint, the decomposition of the space into irreducibles. Now there's a continuum of irreducibles. It's called continuous spectrum. Continuous spectrum. Continuous spectrum is, we're having some fun, if you, yeah. No, we're always having fun. This is a continuous spectrum. So this, yeah, I'm saying all kinds of words that I'm not going to take the time to define right now, but I just want to plant some seeds of what's going to happen. What's going to happen? So, okay, so this is a way of viewing Fourier analysis on the line, not as a direct sum, but as an infinite integral over these over this continua of vector spaces, irreducible subspaces, which have functions that are themselves not in L2, but they occur in the decomposition of L2. We'll get to what I mean by that. What we're really headed towards is something like L2 of the Adels with respect to our Adelic-Haar measure. And in fact, I don't want this whole space. I want the space that's invariant under Q cross. Can I decompose this into irreducibles? We have the action, so A cross acts on here. The multiplicative Adels act on here. We're going to come back to all of this. I'm just planting seeds. I realize you probably don't see everything about what's happening. And decomposition into irreducibles is exactly what we'll call automorphic representations of GL1. And the even bigger picture is that we can do this on GLN, not just GL1 of the Adels modulo GLN of Q, with an appropriate measure that we have to discuss. So this is the case of GL1, and the group GLN acts again on this vector space, and which sub-representations occur in the decomposition is the question of the Selberg 1/4 conjecture, the Ramanujan conjecture. This is big stuff. And of course, there's nothing special about GLN. You take any, so the biggest picture in some sense is you want to take L2 of any reductive group with a whole bunch of other adjectives, and then decompose this into irreducibles. And then instead of the Adels over Q, you can do Adels over number fields, Adels over a global field. And that's sort of the biggest. And then you can play games on these representations. So this is where we're getting to Langland's functoriality. There are games, you can take a representation of this group, and does there correspond to that representation, an irreducible in some in the decomposition of L2 of the representation of the group. Okay, so I think I've gone far out enough. Let's bring it back to down to earth. Okay, but the point is, this silly game that we're playing with a vector space of dimension 4 is not silly at all. It's the whole game, just when we play the same game in a more complicated setting. Okay. It's just a group. This G of A is just a group. So I want to understand L2 G of A. L2 G of A is somehow it has too many representations in it. In fact, in some sense, so in the case of, let's say, GL2R, just to make things a little simpler, we've known all of the irreducible representations of SL2R for 70 years. Which ones arise in the decomposition of the space that's invariant under SL2Z is still, I mean, it's not that mysterious. We know a lot of things about that decomposition, but yeah, so we're going to get to that. We're going to get to that. Okay, now, this is a little bit of foreshadowing. I have to talk about Dirichlet characters, but I have to make it interesting for those that already know Dirichlet characters. So I thought I would. It's just a general thing we can do for any group. For any group, this is what I was saying here. You take any group, you have to have some kind of Haar measure on it. So you want, local compact, yada yada. So there's a Haar measure. And then you look at the square rootable functions on the group, have G act on this. The regular representation acts, and you want to decompose that into irreducible. Why would you want to do such a thing? Because that's exactly what we do in Fourier analysis, and then what we're building up to is the same exact story for automorphic representations, and not just classically, but adelically. So, okay, let's finish our decomposition of this example into irreducible. So we found one irreducible subspace. Now we know that we can look at the orthogonal complement. Can we think of other? I think it's useful actually to stare at what the thing is doing, because Jishan, you had an interesting idea about 1 and 5 sticking together, and 7, 11 wanting to stick together. But if we just make it 1, 1, 0, 0, that's not an irreducible space. Aha. Yeah, what about +1, +5, -7, -11? Right? Because then the 1 and the 5 stay together, the 7, 11 stay together, but then they might have to switch places. And if they do, then they switch signs. So let's try another. So back to Z mod 12 Z cross and the L2 of that. We found in here the vector E1, which is 1, 1, 1, 1, the indicator of 1 plus I'll just write 1, 1, whoops, that's not 1, 1, 5, 7, 11. And now we're suggesting another vector, which is 1 plus 5 minus 7 minus 11. Let's check. So what happens to this vector? So what happens to this vector under 5? Where does 5 take E2? So it takes E2 to 5 plus 1 minus 11 minus 7. So it takes E2 to itself. Where does 7 take E2? Right? So I'm just multiplying. So it takes E2 to 7 plus 7 times 5 is 35, which is 11. Minus, well, let's check. 7 squared is 49. And that has to be a 5, which is negative E2. So it keeps E2 in the span of E2. And 5 times 7 is 11. So if 5 does it and 7 does it, so does 11. Okay, so yes, this is an irreducible subspace. So now we've broken off W1, which is the span of E1. We've broken off W2, which is the span of E2. Can we find any others? That's a good one. And what's the last one? The only thing that's left over. Yes. Those patterns look familiar. Yes, they do. I hope they look familiar. Now, it's actually an accident because this group is abelian and everything decomposes into one-dimensional spaces. It's an accident that the vectors look similar to the characters, because it's actually not the vectors that we want to look at. We want to look at what the representation does to the vectors. That's where we'll see the true character table. But here we have this accident that it actually has the same, the values here, the pattern of the signs is the same as the pattern of the characters. Okay, so let's get all the way to characters. So what's the character of a representation? Definition: if G anything, it doesn't have to be V. If GW is a representation, or let's say pi, GW is a representation, is a G representation. The character pi of pi is a map from G to complex numbers, given by, it takes G to, well, pi of G is a matrix, right? Pi of G is an automorphism of W. It's something that takes elements of W to elements of W. So it's a matrix. I can express it in some basis. I can take the trace of that matrix, sum of the diagonals, and that doesn't care what basis I took this in, because trace is conjugacy invariant, and that's just a complex number, and that's the character of a representation. Okay, so let's work out the characters of these sub-representations. So what are characters? Well, this is going to be boring because it's going to be exactly, you'll see the action, E2. What happens on E2? The identity element obviously fixes everybody. 5 takes E2 to E2, 7 takes E2 to negative E2, 11 has to take E2 to negative E2. So we get, so what is, let's just do it for one. What is chi of GW2 above? Chi takes the elements 1, 5, 7, 11. Now, the representation is already one-dimensional. So the trace of a one-dimensional, of a 1-by-1 matrix is the element that's in the matrix. So I don't have to do anything. But the identity element takes E2 to E2, does nothing. The 5 element takes E2 to E2. The 7 element takes E2 to negative E2. And the 11 element takes E2 to negative E2. So that. I was thinking U2 airplanes shooting down balloons. No. Right. Okay, so that's what the character is, but we're not really going to see it. Let's see. Can I give you an example where we will see characters being genuinely different from the representations? Can we do an example? I think we can. Does this make sense? Have I lost all of you or just some of you?
What do you do with
We're gonna get there. Yeah. So, well, that's what things like trace formula are. That's why it's a non-trivial thing, and it gives you lots of information. Yeah. Should I prove a few more? Let's see. Maybe I should have prepared it. Oh, this stuff is so much fun to play with. We got to do Schur's lemma. Let's do Schur's lemma. Oh, let's do So much to do. Let's do a couple of things. You might have two representations be the same. When are two representations be the same? So definition, if I have two representations, pi 1, which is G acting on a vector space V1, and pi 2, which is G acting on a space V2. If I have a map, I don't know, iota from V1 to V2, if this is a homomorphism, let's say, before we speak of isomorphisms, a homomorphism such that what do I want? Well, I want a commuting diagram somewhere. So if I have an element of V1, D in V1, I can send it by pi of G to another element of V1, right? Pi G V1. This is in big V1. I can also map this down to iota. By iota, I can map this down to V2. So I have iota V in here. Some of you love chasing diagrams and some of you hate it. So I'm going to do this a little slowly for those that like myself, took a little time to appreciate what these things are. So then I can take iota of pi of G V1. That'll be an element of V2, right? Iota sends elements of V1 to elements of V2. This is a linear map. This is a linear map. This is a linear map. I also have pi. This is pi 1. I also have pi 2 of G, which could send this iota V2, pi 2 of G, to iota V. I guess this was I was calling this V1. Iota V1. And that's another element of V2. And of course, these two have to be the same. Such that, so let's write it like this. Iota pi 1 is equal to pi 2 iota. Okay, so this is the property that the representation, whatever the representations are doing, is respected by the homomorphism between vector spaces. Okay, if I have this, then we say, then iota is an intertwining operator. Intertwining operator between V1 and V2. It intertwines the action of V1 and V2. Okay, if iota is not just a homomorphism, but an isomorphism, homomorphism is just a linear map. It might have a kernel. There might be things that go to 0, it might not be injective, or it might not be surjective. It might not fill out all of V2. In either of those cases, it's just a homomorphism. But if it's an isomorphism, it's a bijection. Then basically we just have two different bases for the same thing, and G is actually the same action. So we call pi 1 and pi 2 isomorphism. So this is a definition. This is still a definition. Definition. If the intertwiner is an isomorphism, then the representations are isomorphic. Then we say pi 1 and pi 2 are isomorphic. Okay, so two representations on completely different vector spaces. There's no relation between I1 and I2. Whatever they're doing on those respective vector spaces, if there's an intertwiner that's an isomorphism, then we'll say that those representations are the same. Okay. And so really we want to understand irreducible. So now let me write another thing. This is the unitary dual. This is the unitary representations, unitary irreducible representations, unitary, more generally unitizable, reducible representations up to equivalence, up to isomorphism. Because a unitary representation is just mapped from G into some vector space, but now I have a way of telling when maps into different vector spaces actually is one and the same. Okay, so understanding what the unitary dual is for general groups is very interesting. It's just something. Yes, it's just this. This is the unitary dual. It's just the set of all irreducible representations up to equivalence. And understanding, putting a topology on this thing, these are all interesting things to do that we might get to. Sorry? No, if I have two representations, irreducible representations. That's right. That's right. It's misleading when it is. Yeah, the fact that the characters form a group. So the characters do form a group, but the representations themselves not necessarily. Jishen, you wanted to say something? Yes, if G is finite abelian. Okay, so we're about to get to. I guess I should prove to you that if it's abelian, then then we have one-dimensional. Then the irreducibles have to be one-dimensional. So let's get some Schur's lemmas on here. So this is a lemma of Schur. Sorry? Yes. Yes, that's right. In fact, maybe we'll work out that if we have time. Let me get these sort of classical things out of the way, which apparently you've all seen Schur's lemma because you've all seen representation there. But if G, I guess I'm trying to say W is the irreducible, and if and G W2 is irreducible, bless you. And I have an intertwiner, and I have an intertwining operator, intertwines pi1, and pi2, and is not the zero map, and iota is not equal to 0, then it's not just a homomorphism. So it starts out being just a homomorphism. It has to be an isomorphism. Then iota is an isomorphism. Then iota is an isomorphism. There's no way to intertwine between two irreducible representations unless you're just saying that they're equivalent. Or send it to 0, yes. And the proof is very simple. You look at the kernel. So what do we mean? What do we need to have an isomorphism? I need to be surjective. If iota is not surjective, then the image of iota is an invariant subspace of W2. W2 is G invariant because it intertwines. So G moves elements of W1 around, but the image of iota is going to be some subspace of W2, a proper subspace. That's G invariant. That's not allowed. We said W2 is irreducible. But W2 is irreducible. What if iota has a kernel? What if it's not injective? If it's not injective, then it's a linear map, so then it has a kernel. Then the kernel of iota, which is the set of things in W1 that go to 0, is also invariant. If they map to 0, then this is an intertwiner. So G preserves this kernel. This is also G invariant. But W1 is irreducible. It's about as simple as a theorem as they get. Okay, so both W1 and W2, if pi1 and pi2 are irreducible representations, any intertwiner is actually an isomorphism, unless it's the 0 map. Okay, and a corollary, this is another lemma of Schur. How do I want to say this? If I have a non-zero intertwining isomorphism, if pi G W is irreducible and iota is a map from V to V, that's an intertwiner, intertwining and non-zero. Thank you. Okay, if I have an irreducible representation and some automorphism of the space. that's an intertwiner, what must it be? This is I have to be a little careful here. Okay, let's just keep going. If I have an irreducible space, let's say I have a finite dimensional, although that's not it's not necessary, but the proof that I have in mind, it'll be easier if I have a finite dimensional representation, and the examples we'll have, at least at first, will be finite dimensional. Okay, so if I have a finite dimensional irreducible representation of some group G, and I have an intertwiner operator that's not zero, then that operator can only be one thing, C. Then this is some constant multiple times the identity. Then there exists a constant such that iota, the only intertwiner of a vector space that intertwines an irreducible representation with itself, is the constant multiplication. This is Schur's lemma. Okay, and the proof is, well, I have this iota. Iota has it's a linear space on a linear it's a linear map on a finite dimensional space. So it has at least one eigenvalue has at least one eigenvalue, C and C. So iota minus C has a kernel, which is at least one dimensional, and iota is G invariant. The constant multiple is G invariant, and kernel, then this kernel is G invariant. So it must be all of G. Implies the kernel is all of W, rather.
Why does this proof not work exactly the same way for infinite?
That linear, you have to say a little bit more to get at least one eigenvalue. There are linear maps on infinite dimensional vector spaces that like. Okay, so once we have those two things, now I can prove that if you have a abelian, so lemma, corollary or something, if G is abelian, the reason we had in all of these cases, in all of the Fourier discussion, the reason that these irreducible subspaces are all one-dimensional is because the underlying groups were abelian. The circle is an abelian group, the real line is an abelian group. These are one-dimensional spaces that we can decompose our functions into. We have nice bases for these things. There's a reason for that, which is that if G is abelian and pi is irreducible, then W is one dimension. Okay, the only irreducible subrepresentations of abelian groups are one dimension. And the proof is very simple. So let's G and H be in G. Pi G is a map from W to W. What happens if I apply pi H to pi G? So pi G is my iota. Pi H applied to pi G is pi of HG, but the thing is abelian. So this is pi of GH. The group is abelian, so I can multiply in either order, and it's an action. Yes, let's sort that out. It's correct on functions, not on elements. Yes, correct on functions. That's right. If I flip both of them, it still flips to the other side. The point is, now I have pi H iota composed with iota. Iota is pi G is equal to iota composed with pi H. So pi G is itself an intertwiner. Okay. So pi G intertwines for any G, for any fixed G, pi G intertwines W with itself, or pi with itself, But Schur tells us then pi g is just multiplication by some constant depending on g. Some constant depending on g times the identity. Well, this has a kernel. Any vector, so any v in W is invariant under G because it just gets multiplied by some element. It stays in the same direction. Any v in V spans an invariant space. Spans an invariant space. Subspace. Well, if the thing's going to be irreducible, then V had better span all of W, which means V spans the span of V, which I guess I'll write as CV, is W. Okay, so that's what was happening. Yeah, question.
Why doesn't like you take finite, you take an average, that's going to be by subspace.
Okay, so let's do. I think we have enough time to try to work out to see one non-abelian example. Okay, what happens for a non-abelian example is so the G is just not an interpointer. Pi G is not an interpointer, and there could be higher dimensional irreducible representations, and it will happen. Okay, so let's do one example.
Yeah, I've seen it in production.
Oh, there's always going to be the trivial representation, which fixes. Yeah, so the average over a finite group will always be an irreducible subspace, a one-dimensional irreducible subspace.
Right.
This says if I have an irreducible space, then it must be one-dimensional if the group is abelian. If the group is not abelian, the constant function is still a one-dimensional irreducible subspace. But there could be other irreducible representations that are not one-dimensional.
I see.
This says if it's abelian, then the dimension is one, not if all, well, actually it is true that if all the dimensions are one, then the thing's abelian. But yeah, let's do an example. Let's try to do an example of a non-abelian group. And the smallest one I like to play with is SL2 F2. Okay, because this will be, I haven't decided yet, but I think we're gonna understand groups like this very well and try to understand their irreducible representations and subspaces and so on. Okay, so what is this group? Well, this group is actually very, very simple. What does it mean to be SL2 on the field of two elements? What are the elements? What are the elements of G? I need some 2x2 matrices with zeros and ones and determinant not equal to 0. Because not equal to 0 is the only thing that you could be if the determinant's not 1. Well, I have the identity matrix. What else? 1, 1, 0, 1 is a perfect determinant 1 matrix. We got another one. 0, 1, 1, 0. That's a good one. 0, 1, 1, 0.
Okay, hang on.
No, -1 is the same as 1.
Here's a lower triangle.
How about lower triangular? What else?
Take one stop to be 0 and have the rest be.
That's right. So there's this thing with a 1 over there and the same thing with a 1 over there. And that's all of them. These are all the matrices with zeros and ones in their entries with determinant not equal to 0. So what is this as a group? It's S3. Well, it has 6 elements. Its only choice is a cyclic group of order 6 or S3. You can check that. So what's the order? This thing has order 2, because this times itself is 1, 2, 0, 1, and 2 is 0. So we're back to the identity. This obviously has order 1. How about this guy? It's still order 2. It's still order 2. How about this guy? Order 2. Well, so these must have order 3. These two must have order 3. Okay, and you can check. You multiply this by itself, you don't get the identity, but you multiply it one more time, you do. It really matters whether your zeros are on the main diagonal or not. Yes. Yes. Okay. This group is also the group of S3 is D6. S3 is the same thing as D6, which is the group of symmetries of a triangle. So what can you do with a triangle? You can rotate it by 120 degrees. That's these guys. This is a 120-degree rotation. This is negative 120-degree rotation. Or you could, what's that?
Keep it the same.
You can keep it the same. That's the identity element. That's right. Absolutely. It's there. It's an important one. Or you could flip it down the middle and you have three middles. And that's what these three guys are. Okay. So you can really do this, with your hands. Okay, great. So now we have L2G. L2G is a 6-dimensional vector space. Each of these, now it's going to be annoying to keep track of the matrices. So let's represent this using S3 or D6 as elements A and B, where A has order 3, B has order 2, and it's non-abelian. So whenever I have B times A, I should replace that by A squared times B. Okay, so we can, there's a intertwine, or there's a representation of, we could call this guy A and this guy B, and then you work out who everybody else is.
Not to forget the fact that we chose to write it as SL2 of F2 and just work with it in this abstract group form.
We will absolutely do that.
Okay.
When we get to SL2 F5, we will not want to work with its abstract. Well, actually, it's still, I could bring in an icosahedron, but it'll get more, or P, then I have to say PSL2, because then it gets, yeah, then there actually is a difference. Okay, so how can we decompose this 6-dimensional vector space into a nice basis? We probably won't have time to do it today. So find a nice basis. Find a nice basis for L2 of G that respects the G action. That's invariant. Well, not individually, but I'm just saying more words that mean decompose this into irreducibles. Nice basis for this, giving invariant subspaces, invariant G subspaces, G spaces, G representations. Okay, so you gave us one already. Here, you gave us one, which is, okay, G-Shen gave. Let's see. So the obvious basis is, so the group basis is A squared. I have a B. I don't have a B squared. I have an AB. I don't have an, and I have an A squared B, and that's it. And who has order 3? There are 2 elements of order 3. That's these guys have order 3. And there are 3 elements of order 2. So these guys all have order 2. Okay, so our first invariant subspace will be E plus A squared plus B plus AB plus A squared. That certainly is invariant. Whatever G does, it permutes the things around. So when you sum them all, you don't get anything different. Okay, this is invariant. So here we have W1 and then the rest. Now, how are we going to decompose the rest? So this is where it's helpful. Subtract the order 3 things. So tell me what you mean. Okay, so let's try E2, which is E minus A squared plus B plus AB plus A squared B, right? Okay, there's one problem with this already, which is that this vector is not orthogonal to E1. Because look at the inner product. I have a 1, minus 1, minus 1, 1, 1, 1. I have too many ones.
Want to do something with the cube root?
We definitely want to do something with a cube root of unity, but we could actually get, before we get to the cube root of unity, we can get one more one-dimensional representation out. But let me tell you why I know that there's one more one-dimensional representation. Okay, if we look at the characters, whatever the irreducibles are, so let's go back to the general setting. If G, V is the regular representation, V is the regular representation, and V decomposes into W irreducible representations. These are all irreducible. I claim, I'm sorry, with multiplicities, that's right, irreducible, not necessarily, in fact, what I'm about to claim will show you that it's not, certainly not non-isomorphic. So there might be multiple copies of the same representation. My claim is that the number of times things isomorphic to WK occur in this decomposition in star is equal to anyone know what I'm, anyone who doesn't already know the answer can tell me the answer, what you think the answer might be. I'll just tell you, it's the dimension. So this is rather easy to prove. I guess I need the orthogonality of characters. Okay, so fact, but that's also easy to prove. Come on, fact. So first of all, the character on V is the trace of V, right? We're summing. What is the character on V, by the way?
Sorry,
Yes.
does this claim that there can only be one instance of a one-dimensional subspace?
Yes.
We had many one-dimensional subspaces.
Yes, and they were all all of the one-dimensional subspaces were non-isomorphic. The way pi acts on all of these was different, and one way you can tell that is that the characters were all different.
Okay.
Yes. Okay, so I'm obviously going to run out of time. What's the character of the regular representation? Let's work that out first. The regular representation just moves everybody around. Okay, so what's the character table? So what's the character? So I need to know what it does on E, and then on A, and on A squared, and all the other guys. Well, what is rho of E? Rho of E just doesn't do anything, right? It just fixes everybody. So what's the trace of that? 6, yes. So that's the dimension of V, which is also the number of elements of G. When there's an A, now we're moving everybody by A. How many things are fixed? None. Nobody's fixed. There's nothing on the diagonal. It's all zeros on the diagonal. So actually it's zeros everywhere else. Okay, so the character table for the regular representation is very simple, or the character, not character table, the character table is the list of all characters of irreducibles. The character of the regular representation is very simple. It's G on the identity, size of G on the identity, and 0 everywhere else. Okay, now what about, so these, you can think of V as I mean, it is a vector space, and we've decomposed it into these orthogonal pieces. So character means trace. So this character is nothing but the sum of the characters of the WJ. Right? If I take the traces of the blocks don't interact with one another. So that's a sum of the characters. And so how many times will WK occur? Well, that's if I take, yeah, so I do need the, so this is fact 1, fact 2, and I'm very quickly, yeah, maybe I shouldn't rush this and we could continue this discussion. I just wanted to have a quick little thing about representation theory to motivate Dirichlet characters and then go back to doing analytic number theory. And here we have, I guess you can't do representation theory in one lecture. It's a whole course is worth this stuff. Fact is that if you have, if W1 is not isomorphic to W2, and they're both irreducibles, then the character of W1, I didn't tell you what the inner product on characters is. This is an average over the elements of G when you have a finite group, and obviously we have to fix this if you have an infinite group, of the character on G chi W2 bar. Just the obvious thing. We have complex numbers. We have a sequence of complex numbers, one for each element of the group. So you just multiply them and add. Then this, if they're not irreducible, then this comes out to 0. And if they are, this is 0 if W1 is not, which means pi 1 is not isomorphic to pi 2 and 1 other ones. So this is the orthogonality of characters under this inner product. 0 if they're not isomorphic. Thank you. 1 if they are. And so so why does the number of times that this occur here equal to its dimension? That's because if I take the inner product, so the inner product of chi W of one of these WJs with chi V will measure, this is the number of times, so this is a sum over J prime, chi WJ, chi V, chi WJ prime, which is 1 or 0, depending on if WJ is isomorphic to WJ prime or not. So this is the number of times WJ or something isomorphic to WJ occurs in V. On the other hand, if I take the inner product of chi V with itself, sorry? I divided by the size of G. So this is 1 or 0. So I get a 1 when they're isomorphic, otherwise I get nothing. Oh, here, I'm sorry. Thank you. Yes. So let's see. We know what chi is. So I have a 1 over G times a sum over the elements, but chi V is 0, except for at the identity. At the identity, it has size G for both of them. And so it's just size of G. Right? On the other hand, if I use this fact, so it's a sum over J of chi WJ inner product chi V, I really shouldn't be rushing this. This is the number of times pi J occurs here. So this is a sum. This is a sum over J, and then the number of times. I'm proving something else. I'm proving that the sum of the squares of the dimensions of the distinct irreducibles adds up to G. Darn. Yeah, this is what happens when you rush. Okay, we're gonna pick up with this. What this is about to prove is that next time, I don't know why I thought I could do this in one lecture. Next time, if W1 through WJ are irreducibles occurring in the regular representation without multiplicity. So this is our distinct irreducibles occurring in the regular representation. Then the dimension of the WIs squared adds up to the size of G. And that'll help us with the character table of S3. I'm sorry. I should either go much slower and do this stuff properly, but then we'll suffer when we won't suffer. We'll just do it more slowly.